Welcome to the notes on 5.1 complex numbers and operations. There is a suggestion that you watch this video called Complex Numbers Introduction to Imaginary Numbers. It is less than a 5-minute video and will give you a little bit of an overview of the new numbers that we're going to be talking about today. So, when we, in the last section, when we were given problems like x squared is equal to negative 16, and we were solving for the values of x, we would take the square root of both sides, and we'd get x is equal to plus or minus. And then when I was taking the square root of a negative number, we were writing no real solution, because there is no real number that is the square root of negative 16. Well, today we are going to expand our number system to include the complex numbers and the imaginary numbers. And now we are going to be able to actually solve this problem like x squared equals negative 16. Okay, so it says in order to be able to take the square root of negative numbers, we have to extend our number system to include imaginary numbers and hence something called complex numbers. So there are two different diagrams here for you to kind of look at a little bit. The one on the left is more spatial and the one on the right is more linear. I'm just going to talk by them. So pick one to look at, and then I'm just going to describe a little bit and go through our different sets of numbers that we have. So the very first set of numbers that we work on studying as children are what's called the natural numbers. And if you were to ask a child, a 4-year-old, to start counting, they would start counting by saying 1, 2, 3, 4, and they would keep increasing by probably whole integers. So those are the natural numbers, the natural place to start counting their whole numbers. The whole numbers is the next set, and it includes 0. So if the natural numbers start at 1, the whole numbers are all of the natural numbers and 0. The next set of numbers are the integers, and the integers include the natural numbers, their opposites, and 0. So it includes like negative 5, negative 4, negative 1, 0, and then 1 and 2 and 20 and 22, numbers like that. So natural numbers are whole numbers. Whole numbers are integers, okay? And then when we build out from knowing negative numbers, we start talking about fractional numbers and decimal numbers. So that's what's called rational numbers. So the rational numbers is any number that can be written as a fraction with whole numbers in the top and in the bottom. So when I'm talking rational numbers, think like 1/2, all right, or 1/3. Even though 1/3 is a repeating decimal, because it repeats, it can be written as a fraction. It is rational. All right. Even a number like 8/7, right, which is not a very short decimal, but it can be written as a fraction. If a number is not if a number is not rational, the other side of that coin we then learned was about irrational numbers. And you really start talking about irrational numbers a little bit in Math 1, more so in Math 2, and that idea will grow. An irrational number is a number that doesn't end as a decimal, that doesn't end and doesn't repeat. Okay, so famous irrational numbers are pi or the square root of 3. Okay, they cannot be written as a fraction of a whole number over a whole number. Right, and their decimals do not end or repeat. Now, all of those that we've ever talked about are all the real numbers. These are numbers that we can measure and kind of conceive and put on a number line. Today, we start talking about imaginary numbers. So it's a whole nother scope to look at here. The imaginary numbers exist only because of taking the square root of a negative number. So right down here in blue, it says the imaginary unit I is the principal root of -1. So here I have it written kind of in this script writing. It's very often written kind of like this I right here. It's like italicized. You'll see it if you look at the diagram on the right, kind of how that's written there. That's the I symbol. Okay. So that is actually a number. This I is equal to the square root of -1. So these are two facts that you're going to need to memorize because you're going to use them over and over again. All right. So I is equal to the square root of -1. This is what allows me to take the square root of negative numbers. If that is true, so if it is true that the square root of -1 is equal to I, then if I were to square both sides, it must also be true that -1 is equal to I squared. So that's my second fact. -1 is equal to I squared. These are two pieces of information, like I said, you need to memorize and get comfortable with. So examples of imaginary numbers might be 5i. That's an imaginary number. Right? It has an I at the end because you are multiplying by the square root of -1. Or -1i. All right, that is an imaginary number. Or how about I times the square root of 2? That is also imaginary. They're all imaginary because they all have I's on them. All right, so we have the imaginary numbers, and we can add imaginary numbers and real numbers. And when we do that, we get this thing called a complex number. So complex numbers includes all real numbers, all imaginary numbers, and the sum of real and imaginary numbers. All complex numbers can be written as A plus BI, where A is the real part and BI is the imaginary part. So examples of these types of numbers might be 2 plus 4i. That is a complex number. And we will talk about complex numbers this year. We'll talk about them more in future mathematics when you get to graph them and go into them a little bit more detail. The reason we need imaginary numbers for our sake is for when we get into completing the square and solving quadratics. So 2 plus 4i, that's an example. How about, let's see, 10 minus I could be an example of an imaginary number. -3 plus I radical 6, that could be a complex number there. So it has a real part followed by an imaginary part. Now, as we go through and we do a lot of these operations, it's really easy to treat I as a variable, and it will fall under a lot of the same rules, but it's also important to remember that I is actually a number. It is the square root of -1. Okay. So example 1 is to add or subtract. So what I have here in problem A is I have an addition problem. I have a complex number plus a complex number. So for all of these, whenever I have a symbol, like an addition or subtraction symbol in between sets of numbers, I'm going to rewrite it without any parentheses. So the first thing I'm going to do here is I'm going to rewrite this as 4 plus 3i. And then because this is a plus sign, it's not going to change any of my signs in the next set. So this would be plus negative 5 and minus 2i. I'm just going to rewrite it without parentheses. Then I'm going to combine like terms. So I'm going to combine the real parts and the imaginary parts. So I have 4 and minus 5. Those are real parts. They combine and I get negative 1 plus 3i minus 2i. 3 i's minus 2 i's gives me plus 1i. Okay, so my answer is negative 1 plus, and instead of 1i, I'm just going to write I. And I'm going to leave it like that. I'm always going to write the real part and then the imaginary part. Okay, problem B. So again, I'm just adding. So I technically have a complex number plus an imaginary number. So I'm going to rewrite this without any parentheses to start off with. Okay. And then I'm going to combine like terms. So 8, I have no other whole number, so I'm just going to have 8. And then my imaginary numbers, I've got minus 6i plus 5i, and that's going to leave me with minus 1i. So my answer is going to be 8 minus, and then instead of 1i, I'm just going to leave this as minus I. Now C and D have subtraction signs in between the parentheses, so just like I would if these were different polynomial expressions, I'm going to need to distribute that negative through. So let's go through this. For C, I'm going to write down the first number without any parentheses, 9 minus I. And then when I have minus in front of these parentheses, I basically need to change that sign. You can also think of it as distributing through by a negative 1, right? So I have minus 4 and then minus a positive 7i, so minus 7i. And that's the difference between when it's subtraction other than when it's addition. So I look for like terms. I have a 9 minus 4, which gives me 5, minus I minus 7i. So minus 1i minus 7i, that's minus 8i. 5 minus 8i is what this simplifies to. So I ask you to pause this and try D. Go ahead and try D on your own, and then you can check your work when you've got an answer. Okay, so let's see how that went for you. I'm going to copy down the 4 plus 3i, and then I have a negative sign here, so I'm going to change my sign. So instead of negative 5, I'm going to have a plus 5. Instead of negative 2i, I'm going to have a plus 2i. My like terms are then 4 and 5, which gives me 9. And 3i and 2i, which gives me 5i. So my answer, I always write the real part first, so the 9, and then plus 5i. Okay, we didn't use these facts up here that's part of our definition much, these ones that I've highlighted at the very top, but they're going to be necessary as I move on. Example number 2, now I'm multiplying. And then I'm going to write each simplified answer has a complex number in this form, a plus bi. So for problem A, I have negative 3i times 5i. So we're starting off with like multiplying one term times one term, and then we're going to grow. Negative 3 times 5 gives me negative 15. I times I gives me I squared. Now, going back to the definition, you'll recall the square root of negative 1 is equal to I, and negative 1 is equal to I squared. Whenever possible, we will always plug in negative 1 for I squared. So here where I have an I squared, I'm going to substitute in a negative 1. Put a little asterisk here so you know where that came from. I squared by definition is negative 1. Then I multiply negative 15 times negative 1 and I get a positive 15. Because although I looks like a variable, it's actually a number. All right, B. This is a distribution problem, so I have a 4i in front. And I'm going to multiply through to each term in the parentheses. So 4i times 5. 4 times 5 is 20, and I have an I. 4i times negative 5i. 4 times 5 is negative 20. I times I is I squared. Oh, there's that I squared again. I will never leave it as I squared. I always substitute in the negative 1. And the question is often posed, wait, where did the negative 1 come from? How come those are equal? So it just comes from the definition. And I can scroll back up and show you. Way up here, okay, by definition, the imaginary unit is the square root of negative 1 is equal to I. Therefore, I squared is equal to negative 1. Then I continue to simplify 20i. Negative 20 times negative 1 is positive 20. And I'm not going to leave it in this form. I always want the real part and then the imaginary part. So I'm just going to rearrange and write this as 20 plus 20i. I'm just swapping their sides there. In C and D, we get into multiplying two terms by two terms. When we did this before with polynomials, we used this box to kind of help us organize our ideas. We're going to do the same thing here. And we've been using the box for factoring a lot, but remember, this is just multiplying. So we're going to write our expressions on the outside and multiply to get the inside. So I multiply 3 times 2 and I get 6. 6i times 3 gives me a positive 18. Oops. Positive 18i. 2 times negative I gives me a minus 2i. 6i times negative I gives me a minus 6i squared. Now if I take all those and write them out, write out all the terms, you'll come across the fact that plus 18i minus 2i, I still have like terms when I do this. So we talk about how when I multiply binomials, oftentimes I have like terms across this diagonal, and it's no exception in this case. I have like terms again. So I'm going to combine those. 18i minus 2i gives me plus 16i. But now I have more steps to simplify because I have I squared is equal to negative 1. So I keep going. So I replace I squared with negative 1. This gives me negative 6 times negative 1 is positive 6. And then I combine like terms. So I have a 6 and a 6. That gives me a 12. And then plus 16i. You'll notice there's no squared term. I'm going to go a little bit out of order here than what I originally planned. So I'm going to suggest that you take a few moments and work out problem E on your own before we move on to D. So I also encourage you to write the square root of negative 1 is equal to I a whole bunch of times. So you can get used to it and try to train your brain that this is a fact. So go ahead, pause, try problem E, make sure you get an answer, and then check back for the solution. Okay, so for E, as I multiply, I get a negative 3, a positive 12i, a positive 2i, and a negative 8i squared. And if they're in a different order, that's fine. I combine my like terms. And then instead of I squared, I've replaced that with negative 1. And negative 8 times negative 1 is a positive 8. This gives me 5 plus 14i as my answer for problem E. Okay, I'm going to go back up to D. So similar type of problem, there's just a special case here that we're going to talk a little bit about. So when I multiply 2 minus 3i and 2 plus 3i, in my boxes, 2 times 2 is 4, 2 times negative 3i is minus 6i, 2 times positive 3i is plus 6i, negative 3i times positive 3i is minus 9i squared. When I combine these like terms, you'll likely notice that they're opposites. So I have minus 6i plus 6i. Those go away. They cancel. So I have 4 minus 9i squared left. And I squared is just negative 1 by definition. So now I'm left with 4 plus 9, which is just a whole number. Yes. And this is a phenomenon called complex conjugates. So this is a complex number times a complex number. The conjugate part is when the first part is the same, the second part is the same, and the number in between changes. So if you look at these specifically here, right, it follows this pattern 8 plus bi and a minus bi. Right? So when this symbol is the only thing in between that changes, the product is a real number. So when we look at problem F, 2 minus 5i times 2 plus 5i, same thing is going to happen. So pause this, multiply f out, and you should get a whole number answer. If you don't, you did something wrong. Okay, welcome back. If you solved f correctly, the answer you should get is 29. So let me work through it with you, just in case you didn't get that answer. All right, when I multiply it out before I start simplifying, I have 4 minus 10i plus 10i minus 25i squared. And these middle terms right here are opposites. They cancel. They make everything else go away. The 4 minus 25i squared. Instead of I squared, I'm going to plug in a negative 1. And I'm left with 4 plus 25, which gives me 29. Okay. And why do we do all of this? So that we can solve different types of equations. So when we're talking about quadratic equations, we get a negative number on the opposite side. We can now solve this because we know about imaginary and complex numbers. Yay! So example 3, here's 4 different examples where you're going to get x squared equals some negative number and then have to finish solving. So A is very straightforward. Solve this equation. Of x squared equals negative 25. How do I solve x, right? I have to undo the squaring. So I take the square root of both sides. I take the square root of the left and the square root of the right. When I take the square root of both sides, I get x is equal to plus or minus some number. Well, what is the square root of negative 25? Previously, we just wrote no real solution because we didn't know that there were solutions that could be non-real. Now we know better. Okay. So the square root of negative 25, I like to think about that as the square root of negative 1 times 25. Well, according to our definition, the square root of negative 1 is I. So write it again here. All right. And then the square root of 25, well, I know that's 5. So the square root of negative 25 is actually going to be 5i. So x is equal to negative 5i and positive 5i. Negative 5 imaginary and positive 5 imaginary. So for problem B, for B and C and D, actually, I need to isolate x squared first, just like we did in our last problems when I had real solutions. So I subtract 120 from both sides. And that leaves me with x squared is equal to negative 120. I need to get x by itself. So to do that, I take the square root of both sides. When I take the square root of both sides, I get x equal to plus or minus some number. Well, how do I take the square root of negative 120? I can rewrite that as the square root of negative 1 times 120. The square root of negative 1 is I. How do I take the square root of 120? Gonna need to do a factor tree here. Well, let's go with 10 and 12. We've got 2 and 2 and 2 and 3 and 5. Right? Square root of 2 times 2 is the square root of 4. This comes out and becomes a 2. The other three numbers are all singletons. They don't have a partner. So 2 times 3 times 5 I'm going to leave on the inside. So square root of 120 is 2 radical 3. When I write that as my solution, I'm going to write the 2 first, then the I, then the radical. So I get x is equal to negative 2i square root of 30, comma 2i square root of 30. Now you can write this plus or minus, or you could write it out 2 times with one with a negative, one with a positive. It just depends on the program you're using on if plus or minus is an option. I like to write it out so I can very distinctly see that there are 2 solutions. So for problem C, isolate the x squared first. I have a 2 in the way and the 54 in the way. What we practiced last chapter was that if you were not sure which one to do first, then you would look at your SADMEP, which is your PEMDAS backwards, right? And I have to add or subtract first if I can. So I can subtract by 54 to move that over to the other side. And then I will have to divide by 2. I'm going to get x squared is equal to negative 27. I take the square root of both sides. And x is equal to plus or minus, always plus and minus. Then I need the square root of negative 27. So I like to rewrite that as the square root of negative 1 times 27. I know the square root of negative 1 is I. And then I have to take the square root of 27. So the square root of 3 times 3 is 3, radical 3. So I have times 3, radical 3. When I write this, I write the real number and the I, and then the 3. So I have x equal to negative 3i radical 3 and positive 3i radical 3. And one last one for today. Problem D. Negative 3x squared is equal to 48. So to get x squared by itself, I'm going to divide both sides by negative 3. That gives me x squared is equal to negative 16. I take the square root of the left and the square root of the right. So I'm looking for the square root of negative 1 times 16. And the square root of negative 1 is I, and the square root of 16 is actually just 4. So this is going to be plus or minus 4i. X equals negative 4i and positive 4i. Okay, and that wraps up our conversation on real and imaginary numbers.